Today it's me, Aiden McCormick here, and I will be explaining to you how exactly to use an acceleration graph and how to interpret it. But in order to understand this, you must understand the basics of acceleration, and to understand that, it helps to know what velocity and speed are. Now, speed is the rate at which an object moves, and velocity is this exactly, except it changes, it also takes into account the direction. So let's say the speed is 5 miles per hour, but for velocity you'd need the speed and the direction, so 5 miles per hour north per se. Now acceleration is the change in velocity, and so let's say you're going 5 miles per hour. All of a sudden you see a squirrel, and you don't want to hit the squirrel given the fact that you're a relatively good person, so you slow down your car. You're decelerating here, or maybe let's say you swerve to avoid the little animal. You're actually still changing acceleration because, as I said before, acceleration is a change in direction, and because you swerved, you changed direction. So now that we have a basic understanding of acceleration, it's also good to know what deceleration is. Deceleration is the changing in acceleration, but taking into account it being negative. So let's say I'm moving 5 miles per hour. I see an ice cream truck, and it's about to go away, so I have to run towards that truck. I'm actually now accelerating because I was walking before, but let's say the truck pulls away, and I don't think I'm going to catch the truck, so I slow down. That's the act of decelerating by negatively changing your acceleration. Now, let's talk about how exactly to graph this, and the easiest way to do that is to talk about this flat part right here. What this is exactly is, it's funny because on a graph showing acceleration, it's flat. You can see, oh my god, that wasn't flat. It's flat. You know what, let's pretend that's a flat line going from here to here. It's flat. On a velocity graph, it looks something more like this because it's actually going up. See, what you need to know here is from here to 1 second, right there, to the second, to here, to the third second, it's going 6 miles per hour faster than it did before. So from here to here, let's just say the base is 10. Let's say, as of right now, from here to here to here, the base is 10. But it will be changed later. It's 10. So as you go from here, you're now going at 16 miles per hour, because 10 plus 6 is 16. From here to here, you're going 22 miles per hour, because 16 plus 6 is 22. And from here to here, you're going at 28 miles per hour. So in fact, your acceleration, if this was a velocity graph going like this, you'd actually be going up. So that's the best way to explain what the flat is right there. Now we have to talk about the other two things, like what this acceleration portion is. Now, just so that this is a relatively simple part, you're actually moving at, you're moving here, and in this block of time, from here, let me just redraw that, just so that it's a bit easier. From here, this whole block, you're actually accelerating because the graph is in fact going upwards. Now, in drawing this, it is going up, so you can instantly tell that you are accelerating in fact, because none of these numbers here are negative. So let's go back to this line here. Because you're moving from 1 second, given that this axis should always be time, and this axis should be the dependent variable, or for this second, the acceleration. Let's say you're moving from here to here. Now the change in this is about 0.5 seconds, and you're going 1 mile per hour faster. So let's say, now here's where we're changing a base. Let's make this line 10 miles per hour, this baseline right here. This is 10 miles per hour now. So what you need to know is you're going 1 mile per hour faster after 1 second. So let's say at 1 second you're going 10 miles per hour, and at second number 2 you're going at 11 miles per hour. See, it's not that hard. Now let's say you're going up to here, it'd keep going up at around 1 meter per second. It actually would be a bit higher given the fact that this is number 2, but for the sake of it being relatively clear, I made it a variable like that. Now, this portion right here, this one is also a very important portion because in this you're actually decelerating to the point of your base, which it actually does touch the bottom right here. It does touch the bottom of the line of this right here, meaning, in fact, that in touching this, you go back to your base at 10 miles per hour, but you decelerate from whatever this speed was here relative to this speed, you're going down to that. So now for these seconds, I'll clear it just so that you can see it again. From these seconds right here, you're going at your base, which is 10 miles per hour. And then you accelerate back up until whatever the rest of the graph looks like. Now let's say, for instance, the graph slants down like that. This in fact means that, so let me just rephrase what I said right there because I paused the video and did lose my track a bit. At this second right here, let's say you decelerate. Now you're actually moving negatively to where you were originally, which means that you decelerate at such a speed that you actually go below your starting speed. And what that does, it just means that you could actually, maybe if you hit the flat line, which would be, it's really hard to draw. Maybe you hit the flat line, maybe it's 0 right there. Maybe that's 0. If you hit that, you'll be slowing down to a point where you absolutely stop. But if you keep going past that, you're actually backing up, which is an interesting thing about velocity. So now that's going to be very close to what wraps up the topic that I brought up in the beginning on how to plot a graph. But because acceleration is a change in direction, you also need to know how to plot that. And assuming you don't have a computer, the best graph to use would be one that looks something like this. Now we're going to cut this graph into 4 pieces. These obviously won't be perfect, but they'll be close enough. The line in the middle will have to be the line of the flat line. Now let's make this 10 miles per hour. This right here is 10 miles per hour. Now what you need to do here, let's say you're moving at a weird line that looks something like that, or my bad. You're going along like this, la 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 la. Maybe you're going up some hills, whatever. You now, let's say you change direction. This line here being north. Let's put this in numbers. The 4 quadrants: 1, 2, 3, and 4. This line up here would be a line going north. This whole quadrant right here is you going north. Now this whole quadrant, you could say, is you going west. Something along a compass rose that looks like this. The compass rose would look like this being north, south, east, and west. So if this is north and this is west, then this must be south and this is east. So now let's say you go like this, and because because time is constantly going, you have to do everything off the center. So it all have to go like that in this direction. It'd stem out from the center. Now let's say you're going east. On this graph, it actually have to go down if you're accelerating and up if you're decelerating. But if you get past your flat line, that's when it gets a little bit hairy and actually does confuse the graph a little bit, which is a small fault in this graph, but it's not a big deal. But an easier graph to use, in my opinion, would be one that looks a lot like this. It'd be a cylinder, though. So this is a graph of the top. This is a graph of the top, and this is a graph of the side. I know it's not perfect, but hey, I'm drawing this. So let's say you're moving north. This is the top of the graph. You're moving north. Now let's say it looks like this. Let's say all of a sudden you want to change directions so that it looks like that. The new side of the graph, and this works incredibly well on a 3D scale, if this was your first line, it'd look a lot like this, coming out from the base of the center right here. The base being right here. it would stem out from here. And this is what's really